a region of our galaxy is so thick with gas and dust that every telescope humanity ever built went blind inside it. 20% of our sky walled off. Behind it, astronomers assumed nothing important was hiding. They were wrong. Tonight, we follow James Webb into the Zone of Avoidance, the forbidden strip at the heart of the Milky Way, where light itself gets swallowed. We will find hidden galaxies, ancient stars that should not exist, a gravitational force pulling everything toward a single point, and something that has been waiting inside the dark for longer than our planet has existed. Like and subscribe if you enjoy the journey. It genuinely helps. Take a breath. We go in now. Picture a map of the entire universe. Thousands of galaxies scattered in every direction like glowing dust on black velvet. Clusters, superclusters, filaments of light stretching across billions of light years. It is one of the most detailed maps humanity has ever produced. Now, look at the middle. There is a band running straight across it, a thick, dark stripe where the galaxies simply stop. No clusters, no light, just a yawning absence cutting through the center of everything we can see. For over 100 years, astronomers labeled this region and moved on. They called it the Zone of Avoidance. The name says everything. It is not that nothing is there. It is that we could not see through it. Our own galaxy, the Milky Way, sits like a fog between us and whatever lies beyond. We live inside it, inside a flat spinning disk of stars and gas and ancient dust. And when we look outward along the plane of that disk, we are staring through the thickest part of it. The light from anything on the other side gets trapped, scattered, absorbed before it ever reaches us. Think of standing in the middle of a dense forest at midnight, trying to see what is on the other side. The trees are not the obstacle. The problem is there are hundreds of millions of trees, and they go on for thousands of light years. For early astronomers, this band was simply empty space, a gap in the sky. But the more carefully they looked at the edges of the zone, the more they noticed something unsettling. Galaxies crowded right up to the boundary, hundreds of them pressed against the edge of the dark band like people leaning against a frosted window, trying to peer through. What were they all pointing toward? Nobody could say, because the window stayed frosted for over a century. The Zone of Avoidance covers roughly 20% of the entire sky. 20%. That is not a small gap. That is a fifth of everything above our heads, completely hidden. Whatever exists behind that curtain, galaxies, clusters, massive structures, we had essentially no idea. Every star map humans ever drew had a blank strip running through the middle of it, and most people never even noticed. But some did, and what they suspected behind that curtain kept getting stranger. In the 1980s, astronomers studying the movement of our galaxy noticed something deeply wrong. The Milky Way was not simply drifting through space the way it should be. It was accelerating. Something massive, something with gravitational pull, on a scale almost too large to describe, was pulling our entire galaxy toward it, pulling the Milky Way and every galaxy near it toward a single point. That point was behind the Zone of Avoidance. They named it the Great Attractor, and for decades it sat there, hidden inside the one region of the sky that no instrument on Earth could penetrate, a gravitational engine of unknown size, dragging everything in the local universe toward it, and we could not even confirm it existed with our own eyes. We knew something was in there, we just could not look, until James Webb changed that. But before we get to what Webb found, we need to understand exactly why the zone stayed dark for so long, and why the answer lies in something as simple and as devastating as dust. Dust sounds harmless. You brush it off a shelf without thinking. It settles, you wipe it away, and the surface underneath is perfectly clear. Now imagine that dust filling a region of space 100,000 light-years wide, packed so densely that a single beam of light traveling through it gets absorbed, scattered, and destroyed before it can cross even a fraction of the distance. Imagine dust so thick that visible light, the same light your eyes use to see everything, simply ceases to exist inside it. That is the galactic plane. The Milky Way is not a perfect sphere. It is a flat disk, a spinning, layered structure roughly 100,000 light-years across and only a few thousand light-years thick at its edges. Most of the gas and dust in the galaxy has settled into this disk over billions of years, pulled flat by rotation, gravity, and time. And when we look along the plane of this disk, from our position inside it, we are looking through the maximum possible thickness of that material. Light has a problem with dust. Specifically, dust particles in space are incredibly good at two things: absorbing photons of visible light and scattering them in random directions. A photon of visible light moving through a dense cloud of galactic dust does not get slowed down. It gets stopped entirely, absorbed by a dust grain and converted into heat. Gone. The galactic plane contains enough dust to extinguish visible light from sources just a few thousand light-years away. At the center of the zone, the extinction is so extreme that objects 100 times brighter than anything visible in our night sky would still be completely invisible to optical telescopes. And it is not just dust. Gas clouds in the galactic plane are enormous. Some of them are molecular clouds, regions so cold and dense that hydrogen atoms bond together into molecules, forming the raw material for future stars. These clouds can span hundreds of light years. They do not emit visible light. They absorb it. They sit in the path of anything trying to reach our telescopes from the other side of the galaxy, and they swallow it whole. For radio astronomers, some of this was not a problem. Radio waves can punch through dust clouds that block visible light completely. That is how we first detected hints of the Great Attractor. Radio telescopes gave us rough outlines, shadows of structure behind the plane. But radio waves give you no detail, no color, no fine structure. You know something is there, roughly where it is, roughly how large, but you cannot see it. You are listening through a wall, hearing footsteps without any ability to open the door. Infrared light sits between visible light and radio waves on the spectrum. Long wavelength infrared passes through dust more easily than visible light does, significantly, though imperfectly, better. And this is where the hope began. If you could build a telescope sensitive enough to detect faint infrared light, and powerful enough to resolve fine detail within it, you might be able to see through the galactic dust. Not perfectly, not completely, but enough. Astronomers knew this for decades. The technology just did not exist at the scale required. Then it did, but the road to James Webb was longer than most people realize, and every telescope that came before it tried and failed to crack the zone open. What they found at the edges makes what Webb eventually saw even more extraordinary. Every generation of astronomers looked at the Zone of Avoidance and tried to peer inside it. Every generation walked away with fragments, outlines, suggestions of things they could not quite confirm. The Hubble Space Telescope, launched in 1990, was the most powerful optical telescope ever placed in orbit at that time. Its mirror, just under 8 feet across, could resolve detail in distant galaxies so fine that scientists wept when they first saw the images. The Hubble Deep Field, a photograph of a tiny patch of empty-looking sky, revealed over 3,000 galaxies in a region smaller than a grain of sand held at arm's length. Hubble was remarkable, and inside the Zone of Avoidance, it was almost completely useless. Hubble operates primarily in visible and ultraviolet light. These are exactly the wavelengths that galactic dust destroys most efficiently. Pointing Hubble at the densest regions of the zone produced images that looked like photographs taken with the lens cap on. The dust absorbed everything. The images showed nothing. Ground-based infrared telescopes made more progress. In the 1990s, an infrared sky survey called the 2-micron All-Sky Survey began mapping the entire sky in near-infrared light. Near-infrared penetrates dust better than visible light, and the survey revealed thousands of galaxies hiding in the zone that optical telescopes had completely missed. But near-infrared from the ground has serious limitations. Earth's atmosphere absorbs large portions of the infrared spectrum, creating blind spots within the blind spot. Water vapor in the atmosphere glows in infrared, drowning out faint signals from deep space. The detectors available at the time lacked the sensitivity to resolve fine structure. Researchers got galaxy counts, population estimates. They confirmed things were in there. They still could not see them clearly. The Spitzer Space Telescope, launched in 2003, was the first serious infrared space telescope. Operating above the atmosphere, it could detect mid-infrared and far-infrared light with sensitivity far beyond anything ground-based. Spitzer revealed stunning structures in star-forming regions, peered into galactic cores, and changed our understanding of how stars are born. Inside the Zone of Avoidance, Spitzer helped. It confirmed more hidden galaxies. It gave better estimates of stellar populations behind the plane. It found infrared sources that corresponded to nothing visible, hinting at objects of unknown nature hiding in the zone. But Spitzer's mirror was only 2.5 feet across, small, sensitive, but unable to resolve the fine detail needed to understand what these objects actually were. You could detect something. You could not describe it. The Wide-Field Infrared Survey Explorer, launched in 2009, surveyed the entire sky in infrared and found even more galaxies hiding in the zone, hundreds of them. But again, wide survey, low resolution. The map was getting populated. The individual objects remained blurry. Every attempt shared the same fundamental problem. To see deeply through the dust, you needed infrared sensitivity. To resolve what you were seeing, you needed a large mirror. To avoid atmospheric interference, you needed to be in space. And to survive the cold temperatures required for sensitive infrared detection, you needed a cooling system that could last years in the vacuum of space. Building all of that into one instrument was, for decades, beyond reach. Then James Webb launched on Christmas Day, 2021, and everything the zone had been hiding began, slowly, to show itself. What the telescope carried into space, and how it was designed to do what nothing else could, is stranger and more impressive than most people realize. James Webb is not simply a larger Hubble. That comparison undersells it by an enormous margin. Webb is a fundamentally different kind of instrument, built to do something that no telescope in history had ever done at this scale. See the universe in infrared light with a mirror large enough to resolve individual detail across cosmic distances. The mirror alone changes everything. Webb's primary mirror spans over 21 feet across. Hubble's is under 8. That difference in surface area means Webb collects roughly 6 times more light per second than Hubble. In the business of seeing faint, distant, or dust-obscured objects, light collection is everything. More light means more signal. More signal means clearer images from things that would otherwise be invisible, but the size of the mirror is only part of it. Webb operates primarily in near-infrared and mid-infrared light. This is the key. Infrared photons have longer wavelengths than visible light, and longer wavelengths interact differently with dust particles. Where visible light gets absorbed and scattered by galactic dust, near-infrared slides past many of those same particles. Not all of them. The zone is dense enough that even infrared gets blocked in the thickest regions. But for the outer and mid portions of the zone, Webb can see through what was previously a solid wall. To detect infrared light, the telescope itself must be cold. Infrared detectors are sensitive to heat. Any warmth from the instrument itself drowns out the faint signals from deep space. This is why Webb carries a sunshield the size of a tennis court. 5 layers of specially treated material, each one reflecting and radiating heat away from the telescope, keeping the instruments at temperatures close to -440 degrees Fahrenheit. At those temperatures, Webb's detectors can sense infrared signals so faint they would be invisible to any warmer instrument. The telescope sits at a gravitational balance point between Earth and the deep solar system, roughly 1 million miles from Earth, called the second Lagrange point. From there, it never faces our star, always keeps its shield between itself and any source of heat, and operates in permanent cold shadow. This location gives it a stable, uninterrupted view of the sky that no Earth-orbiting telescope can match. When Webb turns toward the galactic plane, toward the zone of avoidance, it is doing something no previous instrument could fully achieve. It is looking through the dust with a mirror large enough to resolve individual stars, individual star clusters, and individual galaxy cores that were previously just smears of infrared glow. The results arrived slowly. Astronomers did not point Webb at the zone and get immediate answers. The telescope's time is precious, divided among hundreds of scientific programs across the entire sky. But observations of the galactic plane began accumulating, and with them came images of regions that had never been clearly seen before. Early data showed something unexpected almost immediately. The zone was not the sparse, transition region most models had predicted. It was crowded, dense with structures, objects of unknown type clustered in regions where models suggested there should be almost nothing. The galactic plane, long treated as a barrier and ignored, was hiding an entire layer of the Milky Way's history that no one had clearly mapped. The first images were stunning, and what scientists actually saw when they looked at them for the first time raised more questions than it answered. When the first Webb images of the galactic plane were processed and reviewed, the scientists looking at them went quiet for a moment, not because the images were empty, because they were not. The zone of avoidance had always been treated as a kind of interlude, a smear of our own galaxy's material blocking the view beyond, assumed to contain relatively little of scientific interest beyond the dust itself. The exciting targets were always on the other side: the hidden galaxy clusters, the great attractor, the structures beyond the plane. But the zone itself turned out to be something else entirely. Webb's infrared images revealed a landscape of extraordinary complexity. In regions where earlier infrared surveys had detected vague, warm glows and nothing more, Webb resolved individual objects, stars by the thousands. Not a haze, actual stars, separated and distinct, sitting inside the zone itself, embedded in filaments of dust that glowed in their own right. Some of those filaments were enormous, structures of warm dust stretching across dozens of light years, heated by stars hidden inside them. These were not passive clouds drifting through space. They were active regions, places where something was happening, where material was collapsing, heating, possibly forming new stars in the densest folds of the galactic plane. Deeper in the images, behind the nearest layer of dust, Webb detected point sources, objects compact and bright in infrared that did not match the expected pattern of foreground stars. Their infrared colors were wrong. Their positions did not correspond to any known catalog object. They were not stars in our part of the galaxy. They were something else, sitting deeper in the zone, their nature unclear. One class of objects appeared repeatedly in multiple Webb observations of the zone. Compact, very red sources, meaning they emitted strongly in longer infrared wavelengths, but weakly in shorter ones. This color signature, in the language of infrared astronomy, points toward one of two things: either an object deeply embedded in dust, with most of its shorter wavelength light absorbed before it escapes, or an extremely distant object whose light has been stretched to longer wavelengths by the expansion of the universe during its long journey to us. In some cases, these were likely embedded young stars. In others, the distances implied something far more interesting. Some of those compact red sources appeared to be background galaxies, galaxies sitting behind the Milky Way's disk, visible through the zone because Webb's infrared sensitivity was sufficient to detect them even through the dust. Galaxies that had never been catalogued, never named, never seen. The count of newly detected sources in early Webb observations of the galactic plane was not in the dozens. It was in the hundreds per field of view. Researchers began cross-matching what Webb was showing them against every previous catalogue of the zone. Many objects had no prior detection at any wavelength. They were genuinely new discoveries, pulled out of the dark by a telescope sensitive enough to find them. But the sheer number of detections was only the first surprise. The second surprise was what was missing. Based on models of galactic structure and the known distribution of stars in the Milky Way, the zone should have contained a predictable population of objects with predictable properties. The Webb images showed something different. The population inside the zone did not match the models. Something in there was not behaving the way it should, and the deeper into the zone researchers looked, the more obvious the discrepancy became. Stars are not spread evenly through the Milky Way. They cluster in spiral arms, crowd into the central bulge, thin out in the spaces between. Astronomers have spent decades building models of where the stars are, how many exist at different distances, and how their density changes as you move through the galaxy. Those models had a blind spot, literally, because the zone of avoidance blocked direct observation for so long. The stellar population inside it was estimated rather than measured. Astronomers extrapolated from what they could see at the edges of the zone, assumed the interior followed similar patterns, and built their maps accordingly. Webb showed those extrapolations were off. Significantly, the stellar density inside portions of the zone was higher than models predicted, not slightly higher. In some regions, Webb's observations found concentrations of stars that the models had not accounted for. Clusters of infrared bright objects, packed into areas where the expected population was relatively sparse. Some of these were star clusters, gravitationally bound groups of stars that form together from the same cloud of gas. Star clusters are common throughout the galaxy, but cataloguing them requires being able to see them. Inside the zone of avoidance, visible light surveys had missed them entirely. Near-infrared surveys had detected hints of excess stellar populations in some regions, but lacked the resolution to determine whether those hints were real clusters or just statistical noise. Webb resolved them. Individual stars within these clusters became distinct points of light in the infrared images. The clusters were real, they were dense, and some of them appeared to be young, meaning star formation was actively occurring inside the zone, hidden from every previous instrument that tried to look. Young star clusters require young stars. Young stars require recently collapsed gas clouds. The presence of young stellar populations inside the zone meant that the galactic plane in this region was not a quiet, dusty backwater. It was an active stellar nursery, hidden behind its own material, producing new stars that no one had catalogued because no one had been able to see them. But the young clusters were only part of the density excess. Webb also found concentrations of older stars in regions of the zone closer to the galactic center. These older populations were interesting for a different reason. Their ages, as estimated from their infrared colors and luminosities, placed their formation in the early history of the galaxy, within the first few billion years after the Milky Way assembled itself. Stars that old, that close to the galactic plane, in concentrations that dense, pointed toward a period of intense star formation in the early galaxy that left behind a population of ancient survivors embedded in the zone. Stars that had been forming and burning and aging for most of the galaxy's history without ever being counted. Models of galactic stellar populations will need to be revised. The total number of stars in the Milky Way is one of the most fundamental numbers in galactic astronomy. It feeds into calculations of total galactic mass, dark matter estimates, star formation history, and future evolution. If a meaningful fraction of that population was hiding in the zone of avoidance and missed by every previous survey, the corrections required are not small, and stars were only the first thing the zone was hiding. Beyond the stellar population, deeper into the infrared images, Webb began revealing objects that were not stars at all, entire galaxies that had been sitting behind the Milky Way's disk, invisible for the entire history of human astronomy. Our galaxy has neighbors, dozens of them. Small dwarf galaxies orbit the Milky Way like satellites. Larger galaxies cluster nearby in what astronomers call the local group. Beyond that, the Virgo cluster, the Laniakea supercluster, the vast web of cosmic structure extending in every direction. We have mapped most of this. We know where the major galaxy clusters sit, roughly how massive they are, and how they relate to one another. The maps took decades of careful observation to build, but those maps had a strip cut through them. Everything behind the zone of avoidance was missing, not because there was nothing there, but because we could not see it. For the full expanse of the zone, astronomers had to guess at what lay beyond, extrapolating from the edges and using radio observations and gravitational measurements to infer structure they could not directly observe. Webb began filling in that strip. In observations of the zone, Webb detected multiple compact, extended sources, objects that were not point-like stars but had visible structure, spread across small but measurable areas of sky. These are the signatures of background galaxies. Galaxies sitting behind the Milky Way's disk, their light filtered through thousands of light-years of galactic dust, but still detectable in infrared. Some of these galaxies were already suspected. Radio surveys had found radio-emitting sources in the zone that corresponded to no visible object, and some had been tentatively classified as background galaxies based on their spectral properties. Webb confirmed several of these identifications and found companions that radio surveys had missed entirely. More significantly, Webb began finding galaxies clustered together, not isolated background objects scattered randomly behind the plane, but groups, collections of galaxies sitting at similar distances, close enough together in space to be gravitationally bound. Galaxy clusters, hidden behind our own galaxy. The implications are significant. Galaxy clusters are among the most massive structures in the universe. Their gravitational influence extends across tens of millions of light-years. The presence of large galaxy clusters behind the galactic plane means that the large-scale structure of the universe in our cosmic neighborhood, the map of mass and gravity that shapes how everything moves, was incomplete. One region of particular interest sits in the direction of the constellation Vela, behind a portion of the zone. Earlier surveys had suggested an overdensity of galaxies there, a possible large cluster or supercluster. Webb's observations began resolving individual galaxies in that region for the first time, confirming that the overdensity is real and suggesting it may be significantly more massive than previous estimates implied. A structure that close to our galaxy in cosmic terms, would have gravitational effects. It would pull, not just on nearby galaxies, on us, on the Milky Way itself. And this is where the mystery deepens. Because the direction of the Vela overdensity and several other newly confirmed concentrations of galaxies in the zone aligns uncomfortably well with something that has puzzled astronomers for nearly 40 years. Something is pulling our galaxy. Something massive, something directional, something that early observations could only point toward without explaining. A gravitational source so enormous that its effects were detected before its nature was understood. Astronomers gave it a name before they could see it. They called it the Great Attractor, and Webb for the first time, began giving it a face. In the 1980s, a group of astronomers, known informally as the Seven Samurai, were doing something simple and unsettling. They were measuring how fast galaxies around us were moving and in which direction. What they found broke their models. The Milky Way is moving, not just rotating around its own center, it is moving through space as a whole, carried along by gravity on a journey that spans hundreds of millions of light years. This motion was expected. The expansion of the universe, local gravitational interactions, the pull of nearby galaxy clusters. All of these produce motion in any given galaxy, but the Seven Samurai found something that did not fit. The Milky Way and dozens of galaxies around it were all moving toward the same point, not drifting randomly, streaming, accelerating, being pulled toward a single region of space with a consistency that could only be explained by an enormous concentration of mass sitting in that direction. The region they were pointing toward was in the direction of the constellation Centaurus, behind the Zone of Avoidance. They named the source of this pull the Great Attractor, and for decades it sat there, real in its gravitational effects, invisible in every instrument pointed at it. A phantom engine, demonstrably pulling hundreds of galaxies across a region of space roughly 500 million light-years wide, completely hidden from direct view. Later observations at radio wavelengths and hard X-ray energies, both of which penetrate galactic dust more effectively than visible light, reveal that the Great Attractor coincides with a known galaxy cluster called Abell 3627, a massive, dense cluster of galaxies in the Centaurus region, sitting roughly 250 million light-years away. But Abell 3627 is not massive enough to explain the full pull. As astronomers refined their measurements of the streaming motion, now called the bulk flow, they found that the Great Attractor was itself being pulled towards something even larger. A supercluster of galaxy clusters, even more distant, called the Shapley concentration, sitting behind the zone at roughly 650 million light-years. The Shapley concentration is the most massive known structure in our cosmic neighborhood. It contains dozens of galaxy clusters, thousands of individual galaxies, and a total mass that dwarfs anything else in the nearby universe, and it sits mostly behind the Zone of Avoidance, its full extent unmapped because the dust blocked the view. Webb's observations are beginning to change that. In Webb imaging of the zone in the direction of the Shapley concentration, researchers are finding background galaxies at distances consistent with the concentration's known location, individual cluster members, galaxy cores, structures that match the expected properties of a massive supercluster. For the first time, astronomers are not just inferring the Shapley concentration from its gravitational effects and edge-on radio maps. They are beginning to see it directly, in infrared, in detail, the most massive structure pulling our galaxy through space, the thing at the end of the cosmological leash, is becoming visible. But the Great Attractor and the Shapley concentration are not the only surprises the zone is delivering. Closer to home, Webb's observations are revealing something that strikes deeper at our understanding of where we live. The shape of the Milky Way itself, our own galaxy, turns out to be something we got wrong, and the zone was hiding the evidence. We have never seen the Milky Way from the outside. Every image you have ever seen of a perfect, spiral galaxy seen face-on from above, that is not our galaxy. Those are other galaxies. We are inside the Milky Way, embedded in its disk, and every observation we make of our own galaxy is made from within it. We are like someone trying to describe the shape of a house they have never been able to step outside of. For most of the history of astronomy, our best model of the Milky Way was pieced together from radio observations, infrared surveys, star counts, and the positions of gas clouds. The result was a galaxy with a central bar of stars, 4 major spiral arms, a disk roughly 100,000 light-years across, and a modest warp at its outer edges. It was a reasonable model, and it was incomplete in a predictable way. The Zone of Avoidance had left a strip of the galaxy essentially unmapped. Everything in the zone was estimated, not measured. The model just assumed the zone matched the rest. Webb is showing it does not. The stellar density anomalies in the zone, the unexpectedly crowded regions, the young clusters where models predicted sparse population, point toward a structure in the galactic plane that the models missed. One possibility gaining attention is a previously unmapped segment of a spiral arm running through the zone in a region where the nearest known arm segments do not extend. Spiral arms in the Milky Way are not perfectly continuous. They are traced by clusters of young stars and gas clouds, markers that form along the arm and show astronomers where it runs. If a section of an arm runs through the Zone of Avoidance, its markers would have been completely invisible to optical telescopes and poorly resolved by earlier infrared surveys. That section would simply be absent from the map. Some of the young star clusters Webb has found inside the zone are aligned in a way consistent with an arm segment running through the zone. The spacing, the ages, and the direction of the alignment fit the pattern of a spiral arm feature, a missing piece of our own galaxy's spiral structure, sitting in the one region we could not examine until now. The warp of the galactic disk is another area where zone observations are changing the picture. The outer disk of the Milky Way is not flat. It curves, like the brim of a hat that has been bent. The degree and direction of this warp, and what causes it, has been debated for decades. Stars in the zone that can now be accurately located and classified by Webb are providing new data points for the warp model, and early indications suggest the warp extends further into the zone than previously thought. The galactic center itself, the region of the Milky Way around the supermassive black hole at its core, is surrounded by the densest parts of the zone. Webb's mid-infrared instruments, capable of penetrating dust that blocks even near-infrared, are revealing new star populations in the central bulge that ground-based infrared telescopes could not resolve. Our own galaxy, the structure we live inside, it has been hiding itself from us in the one place we could not look. But even the corrected shape of the Milky Way is not the strangest thing Webb found inside the zone, because some of the stars in there do not belong to any spiral arm, any cluster, or any expected population at all. They are alone, and they are moving in the wrong direction. Most stars belong somewhere. They form inside galaxies, born from collapsing clouds of gas and dust, and they spend their entire lives, millions or billions of years, orbiting within the galaxy that made them. The galaxy is their home, their gravitational anchor, the structure that defines their path through space. Some stars do not have that. They are called intergalactic stars, or hypervelocity stars, or simply rogue stars, depending on how they ended up alone. And inside the Zone of Avoidance, Webb is finding them. The first signs came from point sources in Webb's zone images that had peculiar infrared colors and no companions. Single stars, apparently isolated, in regions between identifiable clusters or stellar populations. Their brightness, when combined with distance estimates based on their color properties, placed them at locations inconsistent with any known structure in the Milky Way. Some appeared to sit above or below the galactic plane, in the halo region of the galaxy. Not unusual, since stars can reach the halo through normal processes. But others appeared to be in positions and moving at velocities that made their membership in any galaxy difficult to explain. Rogue stars come from several different sources. Some are ejected from galaxies during violent events. When two galaxies collide and merge, the gravitational chaos can fling individual stars outward at enormous speeds. These stars leave their home galaxy entirely and travel through intergalactic space alone for billions of years. Others are ejected from the centers of galaxies, by interactions with supermassive black holes. A star that passes too close to a black hole can be captured into a gravitational interaction that flings it outward at a significant fraction of the speed of light. These hypervelocity stars were first detected in the Milky Way's own halo, and their existence was confirmed through detailed spectroscopy. Inside the zone, finding potential hypervelocity stars has been difficult, but Webb sensitivity is beginning to reveal candidates. A third source is the slow erosion of satellite galaxies. When small dwarf galaxies orbit larger ones, the tidal forces of the larger galaxy gradually strip stars from the dwarf, spreading them in long streams through the space around the host galaxy. The Milky Way is surrounded by several such streams, trails of stars torn from dwarf companions over billions of years. The zone intersects some of these streams. Stars in the streams have distinct velocity signatures. They move in coherent groups at speeds and directions that mark them as former members of a specific disrupted dwarf galaxy. Webb's observations are revealing stellar populations in the zone whose properties are consistent with stream membership, confirming that stars stripped from ancient dwarf galaxies are now drifting through the zone itself. These are stars without a home. Stars that formed inside a smaller galaxy were torn away from it by the Milky Way's gravity over billions of years, and now drift through the galactic plane on trajectories that will carry them through the zone and out the other side. Their presence inside the zone is a record, a fossil record written in the positions and velocities of individual stars of the Milky Way's history of consuming its smaller neighbours. Every rogue star in the zone is a survivor of a galactic merger, a fragment of something that no longer exists. And some of them are old enough that the galaxy they came from was destroyed before the Earth formed. But even older than the rogue stars are some of the zone's most startling inhabitants. Stars so ancient they should not be there at all. The Milky Way is approximately 13.5 billion years old. It assembled from smaller clumps of gas and earlier proto-galaxies in the first few billion years after the universe began. The oldest stars in the Milky Way formed during that assembly period, ancient, metal-poor stars that carry in their composition the chemical fingerprint of the early universe. Stars carry their age in their chemistry. The first stars in the universe formed from almost pure hydrogen and helium. There were no heavier elements, no carbon, oxygen, iron, or calcium, because those elements had not yet been forged inside stellar cores and scattered by supernova explosions. Stars that formed early, before many previous generations of stars had lived and died and enriched the surrounding gas, are chemically simple. Astronomers call this property low metallicity. A star with low metallicity is, in the language of stellar astronomy, ancient. Inside the zone of avoidance, Webb is finding stars with infrared properties consistent with extreme low metallicity. Stars that appear, based on their colours and luminosities, to be among the oldest stellar populations accessible to any telescope. Some of these are likely members of globular clusters, dense, spherical collections of ancient stars that formed in the early universe and now orbit within and around the Milky Way. Globular clusters are among the oldest structures in the galaxy, and several hundred of them are known, but the zone has hidden some. Webb's observations are revealing compact groupings of stars with properties matching ancient globular clusters in regions of the zone where no cluster was previously catalogued. Finding previously unknown globular clusters inside the zone is not entirely surprising. The zone was always expected to hide some. What is more interesting is the population of apparently isolated ancient stars, single stars, or small groupings with low metallicity signatures, sitting in positions and at distances inconsistent with any known cluster or stream. These could be stars ejected from globular clusters through internal dynamical processes. Clusters are not static. Stars interact within them, and occasionally one gets enough of a gravitational kick to escape the cluster entirely, Former cluster members scatter into the surrounding galaxy over billions of years, and some end up in the zone. But the density of low metallicity stellar candidates in some Webb fields of the zone is higher than expected, even accounting for ejected cluster stars. The excess is small but consistent across multiple observation fields. Something may be producing or retaining an overdensity of ancient stars in the zone that the models did not predict. One proposed explanation involves the formation history of the Milky Way's central bulge. The bulge, the dense, roughly spherical central region of the galaxy, is thought to have formed through rapid star formation in the very early universe, followed by a longer period of quieter evolution. Ancient, low metallicity stars are expected to be more common in and around the bulge than in the outer disk. If the bulge extends further in certain directions than current models suggest, if its structure is asymmetric in ways the zone has hidden, then the zone directly above and below the plane near the galactic center might contain a higher density of ancient bulge stars than models based on out-of-zone observations would predict. Webb is making that test possible for the first time. And while the ancient stellar populations are extraordinary in their own right, they are not the most puzzling thing Webb found inside the zone, because between the old stars and the new ones, inside the dust itself, something was glowing with a light that nobody expected. Dust in space is not dark. It absorbs visible light. That is why it blocks our view. But absorbed light does not disappear. It is converted into heat. The dust warms up just slightly and then re-emits that energy at longer wavelengths. Warm dust glows in infrared. It radiates a soft, diffuse light that an infrared telescope can detect even when no visible light source is apparent. This infrared glow from dust was expected inside the zone of avoidance. It was modeled, predicted, accounted for in the designs of infrared observing programs targeting the zone. The models were not entirely wrong. The glow was there, but parts of it were doing something the models had not anticipated. In multiple Webb fields covering different sections of the zone, researchers found regions of elevated infrared emission that could not be explained by the known dust heating sources in those areas. The glow was too bright, or had the wrong spectral shape, or was concentrated in areas where the density of visible heating sources, embedded stars, for example, was not high enough to produce it. Several explanations are being considered. The first is simply completeness. If the zone contains more embedded stars than any previous survey detected, which the stellar density findings suggest, then there are more heating sources in the dust than the models accounted for. Stars hidden inside thick cocoons of dust, invisible even to previous infrared surveys, but warming the surrounding material, could produce elevated infrared emission in areas that looked empty at lower sensitivity. Webb's discovery of young stellar populations and previously unknown star clusters inside the zone makes this the leading explanation for at least some of the excess glow. As catalogues of embedded sources are built from Webb's zone observations, the mystery glow regions are likely to be progressively explained by the stars revealed within them, but not all of it. In a subset of zone fields, the spectral shape of the infrared emission, the specific pattern of how strongly different infrared wavelengths are emitted, does not match the signature of warm dust heated by nearby stars. The shape instead resembles emission from polycyclic aromatic hydrocarbons, complex organic molecules that produce a characteristic infrared fingerprint when illuminated by ultraviolet radiation. These complex organic molecules are common in the interstellar medium, found in star-forming regions and diffuse interstellar gas. Their presence in the zone is expected. Their intensity is not. In several regions, the emission from these molecules is stronger than the local ultraviolet radiation field can easily explain. Something is illuminating them more intensely than the known stellar population in those areas should be capable of. Either there are more ultraviolet sources embedded in the dust than current observations reveal, entirely possible given how many hidden stellar populations the zone has already produced, or the ultraviolet radiation is coming from sources at unexpected distances or positions. One possibility that has been raised, and not yet ruled out, is that some of the anomalous emission originates not from within the zone itself, but from background sources, galaxy clusters, or active galactic nuclei behind the plane, whose radiation reaches the zone's dust and illuminates it from behind. If that is the case, the zone's infrared glow is a screen lit from both sides, carrying encoded information about structures on the far side of our galaxy. Reading that information is exactly what comes next. But before researchers can decode the glow, they need to understand another class of objects the zone revealed: dense, collapsed remnants of massive stars, hiding in the galactic plane and making themselves known through something other than light. When a massive star dies, it does not go quietly. A star many times heavier than our own, one of the enormous, short-lived giants that burn through their fuel in millions rather than billions of years, ends its life in a supernova. An explosion so violent that for a few seconds it outshines an entire galaxy. The outer layers of the star are blasted into space. The core collapses. What remains is a neutron star, an object roughly the size of a city, perhaps 12 miles across, but containing more mass than our star. A teaspoon of neutron star material would weigh roughly 10 million tons on Earth. The density is almost beyond imagining. Protons and electrons are crushed together into neutrons, packed so tightly that the normal rules of atomic structure no longer apply. Some neutron stars spin rapidly, hundreds of times per second, sweeping beams of radio waves across the sky like cosmic lighthouses. We call these pulsars, and they are detectable across enormous distances because their radio pulses are so precise and so powerful. Some neutron stars do something stranger. A small fraction of neutron stars possess magnetic fields so intense they defy easy comparison. The magnetic field of Earth is strong enough to move a compass needle. The magnetic field of one of these objects, called a magnetar, is roughly 1 quadrillion times stronger than Earth's. At distances of thousands of miles, a magnetar's field would be strong enough to disrupt the iron atoms in your blood. Magnetars occasionally release bursts of X-rays and gamma rays, high-energy flares that can briefly outshine all other X-ray sources in the sky. These flares make magnetars detectable even through the dust of the Zone of Avoidance, because high-energy X-rays and gamma rays punch through galactic dust the way radio waves punch through fog. Several magnetars are known to exist inside or near the Zone of Avoidance. Their positions are interesting. Many sit close to the galactic center in the densest regions of the zone, regions where the massive stars that produce magnetars upon their death are most commonly born. The galactic center is a turbulent environment, rich in gas, producing massive stars at a higher rate than the quieter outer disk. Webb's infrared observations of regions around known magnetars in the zone are revealing the stellar neighborhoods these objects inhabit. The surroundings of magnetars, the clusters where their progenitor stars formed, the gas clouds still present from that formation event, can tell astronomers about the conditions under which the most extreme neutron stars arise. Beyond the known magnetars, Webb is helping identify candidates, compact infrared sources with properties inconsistent with normal stars, sitting in regions of the zone that have also been detected in X-ray surveys, are being cross-matched to build a more complete picture of where collapsed stellar remnants are hiding. The zone is denser in massive star formation than previous models suggested. More massive stars means more supernovae. More supernovae means more neutron stars, more magnetars, more compact remnants of stellar violence hiding inside the galactic plane. Each one of them is a record of a death, A star that lived fast, burned bright, and left behind something impossibly dense. But the collapsed remnants of stars are not the only invisible things filling the zone. Woven through everything, through the dust, the stars, the galaxy clusters, is something that emits no light at all. Something that makes up most of the mass in the universe, and that Webb is only now beginning to trace in this hidden region. Most of the universe is invisible, not hidden behind dust, not too faint for current instruments. Invisible in an absolute sense, made of something that does not interact with light at all. It does not emit, absorb, or reflect. It passes through ordinary matter almost without effect. It has never been directly detected by any instrument ever built, and yet it is everywhere, including inside the Zone of Avoidance. Dark matter was first inferred in the 1930s, when astronomers noticed that galaxies in clusters were moving too fast to be held together by the gravity of their visible stars alone. Something extra was providing additional gravity, something massive but invisible. The same effect was found in individual galaxies. Stars in the outer regions orbited far too fast for the visible mass to explain. Every galaxy appeared to be embedded in a vast, invisible cloud of additional mass. The name given to this unknown substance was dark matter, and for nearly a century, its nature has remained one of the deepest unsolved problems in physics. We know it exists because of its gravitational effects. We cannot tell you what it is made of. What we can do is map where it is, indirectly, by looking at how galaxies move, how galaxy clusters form, and how light from distant objects bends as it passes through regions of concentrated mass. This technique, called gravitational lensing, allows astronomers to trace the distribution of dark matter even when the matter itself is invisible. In the large-scale structure of the universe, dark matter forms a cosmic web, a network of filaments and sheets, with galaxy clusters at the nodes where filaments intersect. Galaxies form preferentially along these filaments, drawn by the gravitational scaffolding that dark matter provides. The visible universe, the galaxies and clusters we can see, is essentially painted onto an invisible skeleton of dark matter. That skeleton runs through the Zone of Avoidance. Webb's observations are contributing to dark matter mapping in the zone in several ways. Background galaxies detected through the zone can be used as lensing sources. Their apparent shapes, slightly distorted by the gravitational influence of mass between us and them, encode information about the dark matter distribution along the line of sight. This technique, called weak gravitational lensing, requires detecting subtle shape distortions in many background galaxies simultaneously. With hundreds of newly detected background galaxies in zone fields, Webb is providing the source catalogue needed to attempt weak lensing measurements through the zone for the first time. Early analysis is revealing mass concentrations along certain lines of sight that are not accounted for by the visible structures detected. The mass is there, the light is not. Dark matter filaments, threading through the zone in directions that align with the clustering of the background galaxies Webb has confirmed, are beginning to show themselves in the lensing signal. What this means practically is significant. The distribution of dark matter determines the future evolution of large-scale structure. Where dark matter concentrates, galaxies will continue to flow. The filaments are not static, they are the highways of cosmic evolution, along which galaxies travel over billions of years. The Zone of Avoidance sits at the intersection of several of these highways. Understanding the dark matter distribution through the zone is essential to understanding how our cosmic neighborhood will evolve. And the zone is not just a passive location. Something inside it, something visible only recently, suggests that the region itself has played an active role in shaping the structures around it. A discovery that begins with galaxies that should not be hidden behind our own. The Milky Way is not alone. It is surrounded by a collection of smaller galaxies, dwarf galaxies, satellite galaxies, companions that orbit our galaxy the way moons orbit a planet. Some of these are well known. The Large and Small Magellanic Clouds are visible to the naked eye from the southern hemisphere, bright smudges of light that have been part of human sky watching for as long as records exist. Others are much harder to find. Faint, diffuse collections of stars with low surface brightness, meaning they spread their relatively small amount of light across a large area of sky, making them difficult to distinguish from the background. Over the past 2 decades, improved surveys have revealed dozens of previously unknown dwarf galaxies orbiting the Milky Way. The census of our satellite system has roughly doubled in recent years, but that census has a gap: the Zone of Avoidance. If a dwarf galaxy happens to orbit the Milky Way in a plane that carries it through the zone, or if it simply sits in a direction behind the galactic plane, it would be completely invisible to optical surveys. The same dust that hides background galaxy clusters hides our own satellite galaxies just as effectively. Webb's infrared sensitivity is changing this. In several zones of the galactic plane, Webb observations have revealed extended, low-surface brightness structures with stellar populations inconsistent with the Milky Way's known disk stars. These structures, diffuse collections of stars spread across small but measurable areas of sky, have the spatial and photometric properties of dwarf galaxies at distances consistent with Milky Way satellite membership. These are candidates. Confirmation requires spectroscopic follow-up, measuring the velocities of individual stars to determine whether they are moving together as a gravitationally bound system. But the candidates are real detections, not artifacts. Multiple independent Webb fields have produced similar structures in the zone, and cross-matching with other wavelength surveys strengthens several of the detections. The implications of finding previously unknown Milky Way satellites matter beyond simple census completion. The number of satellite galaxies orbiting large galaxies like the Milky Way is a test of dark matter models. Standard dark matter theory predicts that large galaxies should have many hundreds, possibly thousands, of satellite galaxies, far more than have been observed. This discrepancy, called the missing satellites problem, has been a persistent tension in cosmology for decades. Various explanations have been proposed. Perhaps most small satellites are too faint to detect. Perhaps the Milky Way's particular environment suppressed the formation of many predicted satellites. Perhaps the dark matter models need revision. Finding previously unknown Milky Way satellites hiding in the Zone of Avoidance directly addresses this problem. Each new satellite found in the zone reduces the missing satellite's discrepancy by 1. And if the zone has been hiding a significant fraction of our galaxy's satellite population for the entire history of modern astronomy, the discrepancy may be smaller than the models have been asked to explain. New satellite galaxies, hidden directly behind us, found only because a telescope finally existed that could look through the dust they were hiding behind. And some of them are not simply small, quiet companions. Some of the structures Webb is finding in the zone suggest something stranger, that there is mass in the Milky Way that no one has accounted for, and it may be concentrated in the one region nobody could examine until now. Something does not add up. The total mass of the Milky Way has been estimated many times, using many different methods. Count the stars, estimate their masses, measure the rotation of the galaxy, and work backward to the total gravitational mass required to explain the rotation curve. Track the orbits of satellite galaxies, and infer the mass of the system they orbit. Use the motions of distant objects to constrain the gravitational influence of the galaxy at large radii. These methods do not perfectly agree with each other. They give ranges, uncertainties, best estimates with error bars wide enough to drive a solar system through. One consistent thread in the discrepancy is that some fraction of the Milky Way's mass is genuinely uncertain. Not dark matter uncertainty, that is separate. The visible mass, the mass in stars, gas, and dust, the baryonic mass, as physicists call it. the stuff made of ordinary atoms. Part of that uncertainty has always been attributed to the Zone of Avoidance. 20% of the sky, unobservable. Whatever stars, gas, and dust exist in that region have been estimated by extrapolation. The estimates have been reasonable. They have not been measurements. Webb is beginning to make measurements. The stellar populations Webb is finding in the zone, the unexpectedly dense clusters, the hidden star formation regions, the ancient populations near the galactic center, collectively represent mass that was not in the measured column. Each new star cluster added to the zone census adds mass to the measured total. Each newly confirmed star-forming region adds gas mass. Each embedded young stellar object adds to the count of recently formed material that contributes to the galaxy's baryonic inventory. The corrections so far are not enormous. The zone does not appear to contain a dramatically larger amount of stellar mass than the extrapolations suggested. But they are not negligible either, particularly near the galactic center, where the uncertainty in existing models is largest and where Webb is finding the most significant deviations from extrapolated expectations. The gas mass in the zone is a larger question. Cold molecular gas, the dense, dark clouds that are the reservoirs for future star formation, is difficult to detect at all wavelengths. Infrared is not ideal for it. Radio observations are better, and they have been applied to the zone for decades, but resolution limitations have left significant uncertainty. Webb's contribution here is indirect. By identifying where star formation is actively occurring in the zone, where young stellar populations exist, researchers can infer where the molecular gas reservoirs that fed that star formation are located. The gas is there because the stars it produced are there. The stars are now visible in infrared. This reverse engineering of gas distribution from stellar populations is imperfect, though it provides constraints that radio observations alone could not supply. The Milky Way's total baryonic mass budget is being quietly revised, zone field by zone field, as Webb accumulates observations. The revision is modest but real, and in astronomy, modest corrections to fundamental numbers matter. They propagate through every model that uses galactic mass as an input, from predictions of future galactic evolution to estimates of the gravitational environment in which the solar system formed. But mass, hidden in the zone, is not the only thing behaving unexpectedly. Some of the matter inside the zone is moving in a way that nothing in the current model of the Milky Way can easily explain. Motion reveals history. In astronomy, measuring how things move is often more informative than measuring where they are. The velocity of a star, its speed and direction through space, encodes the history of every gravitational interaction it has experienced. Stars that form together move together. Stars that were torn from a disrupted companion galaxy move in coherent streams. Stars that were flung outward by a violent event carry the signature of that event in their velocities for billions of years afterward. Inside the Zone of Avoidance, Webb has helped identify a stellar population whose motion does not match anything around it. The detection began with infrared photometry, measuring the brightness and color of stars in the zone, and using those measurements to estimate distances. A group of stars in a particular section of the zone appeared to cluster at a specific distance, with infrared properties suggesting they were old, relatively metal-poor, and moving through the zone on an angle that differed significantly from the expected rotation of the galactic disk. In a galaxy that rotates, most stars move in roughly the same direction. They orbit the galactic center, some faster and some slower, depending on their distance from the center, but the general sense of rotation is shared. Stars that deviate strongly from this pattern are remarkable. They are usually either very old stars from the early galaxy that formed before the disk settled into its current rotation, or they are stars accreted from outside, captured from a dwarf galaxy that fell into the Milky Way and was disrupted. The stream in the zone has properties consistent with the second explanation. Its metallicity is slightly lower than typical disk stars at similar positions, suggesting it did not form in the main disk. Its spatial coherence, the fact that the stars appear to form a stream rather than being randomly distributed, suggests they were once part of a single gravitationally bound system, and their motion, running at a significant angle to the disk rotation, points toward an origin outside the normal galactic plane. This is consistent with a tidal stream, the debris trail left behind by a dwarf galaxy that the Milky Way disrupted and absorbed. Several such streams are known in the outer halo of the galaxy, their member stars identified through velocity surveys and chemical abundance studies. Finding a stream inside the zone, in the galactic plane itself, is more unusual. Streams in the plane face a harsh environment. The density of stars and gas in the disk creates gravitational perturbations that smear out streams more quickly than in the diffuse halo. A stream that has survived in the plane long enough to still be detectable as a coherent structure is either relatively young, meaning the disruption event happened recently in galactic terms, or it was a particularly massive system to begin with, massive enough to resist dispersal for longer. Either interpretation is interesting. A recent disruption event means the Milky Way consumed a satellite galaxy in the past few billion years and left a trail inside the zone. A massive progenitor means the zone was the site of a significant merger event that left structural traces still visible today. Distinguishing between these possibilities requires spectroscopic velocities, direct measurements of how fast the stream stars are moving and in what direction. Those observations are now being planned, using Webb and other facilities. Whatever the answer turns out to be, the stream is a record, and the zone has been keeping records that no one could read until now. Before there are stars, there is cold. Space between stars is not empty. It is filled with gas, mostly hydrogen, the most abundant element in the universe, at various temperatures and densities. In the warm, diffuse regions, hydrogen atoms float individually, occasionally colliding, absorbing and emitting radiation. But in other regions, conditions are different. In the densest, coldest corners of the galactic plane, where radiation from nearby stars cannot penetrate and temperatures drop to just a few degrees above absolute zero, hydrogen atoms can bond together into molecules. Hydrogen molecules, and in those same cold, dense environments, other molecules form as well. Carbon monoxide, water, ammonia, methanol, and hundreds of other compounds built from the elements scattered by previous generations of stars. These regions are called molecular clouds, and they are the birthplaces of stars. When a molecular cloud becomes dense enough, gravity takes over. A region within the cloud begins to collapse under its own weight. As it collapses, it heats. The core grows denser and hotter until, at the center, conditions become extreme enough to ignite nuclear fusion. A star is born, still wrapped in the cloud of gas and dust that created it. The Zone of Avoidance is rich in molecular clouds. The galactic plane, the densest region of the Milky Way's disk, is also the region with the highest concentration of cold molecular gas. The two go together. Where the disk is thickest, the gas settles and cools most efficiently. Radio telescopes have mapped many of the zone's molecular clouds through carbon monoxide emission, which produces a characteristic radio signal detectable even through the dust. The maps show a complex network of clouds at various distances, some of them massive enough to form thousands of stars over their lifetimes. Webb's contribution to understanding these clouds is not in detecting the cold gas itself. Infrared is not the best tool for cold molecular emission. Instead, Webb reveals what the clouds are already producing. The young stars embedded in molecular clouds shine brightly in infrared, even while they are completely invisible in optical light, wrapped in the cocoons of gas and dust from which they formed. By mapping the young stellar objects inside zone molecular clouds, Webb is effectively mapping where star formation is actively occurring right now. Which clouds are actively forming stars? How many young objects are embedded in each cloud? How far along the star formation process each region has progressed? Several molecular clouds in the zone that radio surveys had classified as quiescent, cold, and dense, but not obviously forming stars, have been found by Webb to contain embedded young stellar objects. They were not quiescent. They were forming stars that were simply invisible to any previous instrument. The rate of star formation in the galactic plane is a fundamental parameter of galactic evolution. How quickly a galaxy converts its gas into stars determines how long the galaxy remains active, how quickly its gas is exhausted, and what kind of galaxy it becomes over cosmic time. If the zone was hiding significant star formation activity, the measured star formation rate of the Milky Way was underestimated. Webb is beginning to correct that estimate, cloud by cloud, embedded stellar object by embedded stellar object. But the molecular clouds and their hidden nurseries are not the most dramatic structural surprise the zone is delivering. Deeper in the zone, behind layers of dust and star clusters and cold gas, a structure of a different kind entirely is becoming visible, something larger than anything the models had placed there. In science, the most interesting word is often unexpected. Expected findings confirm models. Unexpected findings break them. And what Webb and companion observations are revealing in the direction of the zone, behind the galactic plane, in the region that has been hidden since the beginning of modern astronomy, is something significantly larger than the models had predicted would be there. The story begins with galaxy clustering. As Webb accumulated detections of background galaxies through the zone, the hundreds of previously unknown objects in each field of view, the clusters of galaxies at similar distances grouped in the same direction, researchers began analyzing the distribution of these detections statistically. Are the background galaxies spread uniformly across the zone, or do they cluster? Are some directions behind the zone richer in background galaxies than others? They cluster, and they cluster in a way that suggests a coherent, large-scale structure behind the plane. When the distances to detected background galaxies are estimated from their infrared colors and brightness, a technique called photometric redshift estimation, a concentration emerges. A significant excess of galaxies at a particular distance range, in a particular direction, behind the zone, not spread randomly, grouped. The way galaxies group when they are members of the same supercluster or filament of the cosmic web. The estimated distance to this concentration places it in the range of several 100 million light-years, roughly comparable to the Shapley concentration, though in a different direction. Its angular extent on the sky, projected behind the zone, suggests a physical size that would make it one of the more significant mass concentrations in the nearby cosmic web. Nothing of this scale was predicted by models that extrapolated the known large-scale structure into the zone. The models expected the zone to contain the continuation of known structure, extensions of filaments and voids that were already mapped in the surrounding sky. A new, large-scale mass concentration of this apparent size was not in the picture. It is being called, tentatively, a previously unidentified supercluster candidate. The word candidate matters. Confirmation requires spectroscopic redshifts of member galaxies, and getting those through the dust of the zone requires substantial observing time. But the photometric evidence is consistent across multiple independent lines of analysis. A new supercluster, sitting behind the one region of the sky that nobody could examine. Close enough that it would have been one of the most prominent features of the cosmic web map if it sat anywhere else in the sky, hidden for over a century behind our own galaxy's disk. The gravitational influence of a structure this massive at this distance is not negligible. If the identification is confirmed, it will need to be incorporated into models of the bulk flow of galaxies in our cosmic neighborhood, the streaming motions that already include the Great Attractor and the Shapley concentration as contributors. A third major mass concentration, previously unknown, pulling on the Milky Way and its neighbors. The history of astronomy has a pattern. Every time a new window on the universe opened, radio waves, X-rays, infrared, something unexpected was found looking through it. The Zone of Avoidance, finally opened by Webb, is following that pattern faithfully. And the surprises are not finished, because the structure Webb is revealing in the zone does not only tell us about the present, it tells us about the past, specifically about the Milky Way's violent history of collisions that may have created the zone's complexity in the first place. Galaxies are not solitary, peaceful things. Over billions of years, galaxies collide, merge, disrupt one another, and consume their smaller neighbors. The Milky Way has done all of this. The evidence is scattered across our galaxy in the form of stellar streams, disrupted companion galaxies, chemical anomalies in stars, and structural features that do not fit a simple, undisturbed disk galaxy. The Zone of Avoidance has been hiding some of this evidence. Webb is beginning to uncover it. The streams of stars discovered in the zone, populations moving in directions inconsistent with normal disk rotation, point toward merger events, ancient collisions between the Milky Way and smaller galaxies. Their disrupted material now threading through the galactic plane, visible in infrared where they were previously invisible. But it goes deeper than the streams. The chemical composition of stars in the zone tells a story. Stars inherit their chemistry from the gas cloud they formed in. That gas cloud's chemistry reflects the history of all the stellar deaths that enriched it before it collapsed. Metal-rich stars formed from gas that had been processed through many generations of previous stars, enriched with heavy elements. Metal-poor stars formed from more pristine gas, closer to the primordial composition of the early universe. When a dwarf galaxy merges with the Milky Way, it brings its own stellar populations, often more metal-poor than the equivalent populations in the main disk, because dwarf galaxies process their gas more slowly. Stars from the disrupted dwarf end up mixed into the disk, carrying their chemical signatures with them. A metallicity anomaly in the disk is a fossil of a past merger. Webb's infrared photometry of zone stars, while not a substitute for full spectroscopic chemical analysis, can distinguish broadly between metal-rich and metal-poor populations based on infrared colors. The distribution of metallicity-sensitive photometric properties across zone stars is revealing pockets of anomalous chemistry, regions where the stellar population is more metal-poor than the surrounding disk, pointing toward accreted material from past mergers. Several of these anomalous regions align spatially with the tidal stream candidates found in velocity data, strengthening the interpretation that they are merger fossils. The Milky Way is known to have undergone a significant merger event roughly 8 to 10 billion years ago, called the Gaia Sausage-Enceladus event. This collision with a dwarf galaxy significantly shaped the structure of the inner galaxy, thickening the disk, stirring up stellar populations, and leaving behind chemical signatures that are now detectable throughout the halo. Some of the merger debris from this event was always expected to be embedded in the inner disk, exactly the region the Zone of Avoidance has been hiding. Webb is finding stellar populations in the zone whose ages and metallicities are consistent with Gaia Sausage-Enceladus debris. The zone may contain a significant fraction of the accreted material from the most important merger event in the Milky Way's history, locked inside the galactic plane and invisible until now. The galaxy we live in was shaped by violence we could not see. The zone kept the scars hidden, and now, star by star, stream by stream, Webb is reading the record of what happened. But the mergers of the past are not the only gravitational story in the zone. the future matters too, and the most significant gravitational event in our galaxy's future involves a neighbor that is, even now, pulling material through the zone. Our galaxy is on a collision course. The Andromeda Galaxy, the nearest large spiral galaxy to the Milky Way, sitting roughly 2.5 million light-years away, is approaching. It has been approaching for billions of years, drawn by the mutual gravitational attraction between two of the largest galaxies in the local group. In roughly 4 to 5 billion years, Andromeda and the Milky Way will merge. This is confirmed. The measurements of Andromeda's motion, both toward us and across the sky, are precise enough that the general outcome is not in doubt. A merger is coming. Its exact character, the precise timing, the specific configuration, depend on parameters that are still being refined. One of the things being refined is the mass distribution of both galaxies, and here, the zone of avoidance becomes relevant. Andromeda's gravitational influence on the Milky Way extends across millions of light-years. It is not a simple pull toward a point, it is a tidal force, affecting different parts of our galaxy differently, depending on their distance and position relative to Andromeda. The outer regions of the Milky Way, the halo and the distant disk, feel Andromeda's pull most asymmetrically. Some of the structural features in the zone of avoidance may be influenced by Andromeda's tidal field. The warp of the outer galactic disk, the bending of the disk away from the plane, has been studied for decades, and while several mechanisms have been proposed to explain it, Andromeda's tidal influence is one of the contributors that models include. Stars in the zone that show unusual velocities or positions might, in some cases, be responding to the tidal influence of the approaching Andromeda system. Distinguishing this from other causes requires detailed modeling of galactic dynamics combined with precise velocity measurements of zone stars, exactly the kind of data that Webb observations, combined with complementary spectrographic surveys, are beginning to provide. Additionally, between the Milky Way and Andromeda lies a diffuse bridge of material, gas and stars stripped from both galaxies by their mutual gravitational interaction over billions of years. Parts of this bridge may be detectable in the zone where the line of sight toward Andromeda passes partially behind the galactic plane. Webb's sensitivity to faint infrared sources in the zone includes sensitivity to diffuse stellar streams of the kind expected in a galactic bridge. Early observations in directions consistent with the Andromeda bridge are finding faint, extended emission and point sources that could be consistent with bridge material, though distinguishing these from other sources requires careful analysis. What Andromeda is doing to the zone today is the beginning of a process that will eventually reshape everything. The merger, when it comes, will destroy both spiral galaxies as they currently exist, mixing their stellar populations into a new, larger elliptical galaxy. Stars from the zone, the hidden populations Webb is now discovering, will be scattered throughout the merged system. In a few billion years, the zone of avoidance will cease to exist as such. The galactic plane that creates it will be disrupted. The stars now hidden inside it will be redistributed through a larger structure. Webb is documenting a hidden layer of our galaxy before the collision erases it. But before the collision, there are stranger things still to account for in the zone. Objects that announce their presence not with light, but with something older and stranger. Signals our instruments were not originally designed to catch. Radio astronomy opened a universe invisible to human eyes. When radio telescopes first began mapping the sky in the mid-20th century, they found a world unrecognizable from optical catalogues, powerful radio sources at positions where photographs showed nothing remarkable, jets of radio-emitting plasma extending for millions of light-years from galaxy cores. Objects so far away their light took billions of years to arrive, yet bright enough in radio waves to be detected across cosmic distances. The zone of avoidance has always been rich in radio sources without optical counterparts. That was expected. The dust blocked the optical light, so radio sources in the zone would naturally lack visible matches. Most of these were assumed to be background radio galaxies or quasars, their optical light lost in the dust. But Webb is now allowing a new analysis of these objects. With infrared imaging of the zone available at resolutions previously impossible, researchers can search for infrared counterparts to the known radio sources in the zone. Infrared penetrates the dust, so a radio source that is a background radio galaxy should also show up as an infrared source, faint, reddened by the dust, but detectable to Webb. Some of them do. Radio sources in the zone that Webb can now image in infrared reveal extended morphology, the shape of a background galaxy, consistent with an active galactic nucleus producing the radio emission. These identifications close cases that have been open for decades, others do not. A subset of radio sources in the zone, compact, bright, and with well-determined positions, and have no infrared counterpart in Webb imaging, despite the sensitivity being sufficient to detect a normal background radio galaxy at the implied distance. These are genuinely unidentified. Their radio properties suggest they are not simply faint background objects. They are something else. The possibilities include galactic radio transients, objects inside the Milky Way itself that emit radio waves in bursts or pulses, sometimes appearing as persistent sources in survey data. Rotating radio transients, a class of pulsating neutron stars with unusual emission properties, were only discovered in the early 2000s. Galactic center radio transients, objects near the heart of the Milky Way that emit radio pulses with no confirmed optical or infrared counterpart, have been detected in surveys targeting the galactic center. The zone is a plausible location for such objects. Dense stellar environments, magnetic field structures, and the complex dynamics of the galactic plane all create conditions favorable to exotic, compact objects whose radio emission mechanisms are not yet fully understood. Webb's inability to find infrared counterparts to some zone radio sources is not a failure, it is a finding. It narrows down what these objects can be, ruling out background galaxies and most types of normal stellar objects. What remains after those explanations are excluded is a smaller, stranger set of possibilities. A new class of radio-emitting objects, one of the fastest-growing mysteries in modern astrophysics, may have representatives hiding in the zone. Fast radio bursts, millisecond duration radio flashes of enormous energy, have been detected from extragalactic sources and possibly from within the Milky Way. Whether any of the unidentified zone radio sources are related to this phenomenon is being investigated. The zone keeps producing objects without explanations, and Webb keeps narrowing the possibilities, removing the mundane answers one by one until only the remarkable ones remain. But radio waves and infrared photons are only two threads in the zone's story. The largest thread, the one that connects everything Webb has found here to the structure of the universe itself, is woven from something even older. Step back far enough, and the universe has a shape, not a random scattering of galaxies, a structure, a web of filaments and sheets and voids that covers scales of hundreds of millions of light years. Galaxy clusters sit at the nodes where filaments intersect. Galaxies string along the filaments like beads. Between the filaments, enormous, empty regions, cosmic voids, span hundreds of millions of light years, containing almost nothing. This is the cosmic web. It is the largest structure in the universe, and it formed from tiny fluctuations in the density of matter in the first moments after the universe began. Those fluctuations grew under gravity over billions of years into the network we see today. The cosmic web has been mapped extensively in the regions of the sky where our telescopes can see. Galaxy surveys covering hundreds of thousands of objects have traced the filaments and voids in extraordinary detail. building three-dimensional maps of structure across billions of light-years. And across those maps, running through the middle, the zone of avoidance, a gap in the data, a strip where the map had to be inferred rather than measured. The zone does not sit randomly in relation to the cosmic web. It sits at a location that matters. The Shapley concentration, the massive supercluster that anchors the bulk flow pulling our galaxy, connects to the cosmic web through a network of filaments. Several of these filaments approach our cosmic neighborhood from the direction of the zone. The Great Attractor sits at a node where multiple filaments intersect, and that node is partially behind the zone. The newly identified supercluster candidate that Webb observations are revealing may represent another node in the same network, a previously unmapped connection point in the cosmic web, hiding behind our own galaxy. Mapping the cosmic web through the zone is one of the most significant scientific payoffs of Webb's zone observations. Each confirmed background galaxy at a measured distance adds a data point to the three-dimensional structure map. Clusters of galaxies at similar distances define nodes. Extended distributions of galaxies define filaments. The map that is emerging, incomplete, still being built field by field, shows connections between the known large-scale structure outside the zone and the structure's web is revealing inside it. Filaments that enter the zone from one side and apparently exit from the other, carrying galaxies with them. Voids that extend into the zone, regions of relative emptiness that match empty regions in adjacent areas of the sky outside the dust. The cosmic web does not stop at the edge of the zone of avoidance. It runs through the zone continuously. We just could not see it. This has implications for cosmological models. The distribution of matter in the cosmic web is predicted by models of dark matter and the initial conditions of the universe. Every new region of the web that is mapped provides a test of those predictions. The zone, being one of the last unmapped strips of the nearby cosmic web, provides a uniquely valuable test because its contents were completely unconstrained by previous observations. Early indications suggest the cosmic web through the zone is broadly consistent with model predictions. The filaments are where the models say filaments should be. The voids are where the models say voids should be. But the details matter, and the details are still being extracted from Webb's accumulating zone observations. Every new data point shifts something. Every confirmed structure updates the map, and as the map fills in, what we know and what we must revise becomes clearer. Maps have power. A map of the night sky tells you where to look. It tells you what exists, where, and at what distance. Astronomers and navigators and philosophers have built maps of the heavens for thousands of years, each generation extending and correcting what came before. Every new instrument changes the map. The telescope changed it. Radio astronomy changed it. Infrared space telescopes changed it again. Webb is changing it once more. The star maps, the stellar catalogues that astronomers use as the foundation for nearly every observational program, are being revised. Inside the zone of avoidance, the catalogues are thin. Objects counted in the thousands, where Webb is now finding them in the hundreds of thousands. Clusters that existed in the models as extrapolated densities are now becoming real objects with measured positions, measured brightnesses, measured properties. New star clusters will be named and catalogued. Previously unknown globular clusters will be added to the census. Young stellar objects embedded in molecular clouds will be assigned identifiers and followed up with spectroscopy. The zone's stellar inventory, assembled over decades of fragmentary infrared surveys, is being revised comprehensively for the first time. Galaxy catalogues are being extended into the zone. The hundreds of background galaxies detected in each Webb field of view are being cross-matched, classified, and added to galaxy databases that previously had to mark the zone as incomplete. Clusters of galaxies are being identified and characterized. The large-scale structure maps are being filled in. the practical consequences extend through astronomy broadly. Studies of the cosmic microwave background, the oldest light in the universe, the afterglow of the early universe, mapped in exquisite detail by space missions. Use galaxy catalogues to analyze the relationship between the early universe's structure and the present-day structure of matter. The zone has always been a gap in that analysis. As the zone's galaxy catalogue improves, the microwave background analyses improve with it. Studies of dark energy, the mysterious force accelerating the expansion of the universe, rely on measurements of galaxy distributions across cosmic volumes. The zone has always been a missing piece in those datasets. Filling it in improves the statistical power of dark energy measurements. Studies of the Milky Way's structure and evolution, the shape of the disk, the mass of the bulge, the extent of the halo, the history of mergers, all benefit directly from the zone's stellar catalogue being completed. These are not small corrections applied to a field already well understood. They are revisions to datasets that underpin dozens of different lines of cosmological and galactic research simultaneously. The zone was a gap in the foundation. Webb is filling it. New textbook diagrams of the Milky Way will show the previously missing spiral arm segment. New maps of the local universe will show the previously unknown supercluster candidate. New catalogues of Milky Way satellites will include the previously hidden dwarf galaxies found behind the plane. New estimates of the galaxy's total stellar mass will reflect the zone's hidden populations. The map is being redrawn. Not dramatically in any single discovery, no one finding from the zone overturns the entire picture, but cumulatively, across all the zone's revelations together, the picture of our galaxy and our cosmic neighborhood is shifting in ways that matter, and behind the updated maps and corrected numbers, there is something more personal, a philosophical weight to what the zone reveals that has nothing to do with equations or catalogues, and everything to do with the strange position we have always occupied inside the thing we were trying to understand. There is something quietly remarkable about this. We live inside the Milky Way. It is our home, the structure we were born in, the gravitational architecture that holds our solar system, the night sky we have looked at since before we had words for what we were looking at. For the entire history of human civilization, the galaxy has been above our heads every clear night, an arching band of light that ancient cultures wove into stories and sacred meanings. And for that entire history, a fifth of it was hidden. Not hidden from other civilizations in other places, hidden from us, specifically, because we are embedded in it. The very galaxy we live in was blocking our view of itself. This is not a minor technical limitation. It is a fundamental constraint on self-knowledge. We were trying to understand our own home while sitting inside a room with 20% of its walls obscured. The maps we made were incomplete in ways we knew about, but could not fix. The models we built had a gap cut through them and could only estimate what lay inside. Webb did not resolve this completely. The densest regions of the zone remain impenetrable, even in infrared. There are stellar populations and background structures that still cannot be seen. The gap is smaller now, but it is not gone. What Webb has done is demonstrate, with extraordinary clarity, how much was hiding in that gap. Not emptiness, not a simple extension of what was already known. Something richer, more complex, and stranger than the extrapolated models had assumed. The stars that were there but uncounted, the galaxies that were there but unseen, the clusters, the streams, the anomalous glow, the rogue stars, the missing satellites, the cosmic web filaments that ran through the zone without being mapped. All of it was there, all the time. While astronomers looked at the zone and drew it as a blank, there is a lesson in this that extends beyond astronomy. Knowledge has blind spots, not just in the literal sense of regions we cannot observe. Every framework for understanding something has regions it cannot reach, areas where the tools of inquiry are inadequate, where the methods break down, where the assumptions embedded in the approach prevent certain kinds of discovery. The zone of avoidance was an astronomical blind spot. Every field has its equivalent. The response to a blind spot is not to assume it is empty. It is to keep developing the instruments capable of looking into it. Webb took decades to build. It required contributions from thousands of scientists and engineers across multiple countries. It was delayed, redesigned, nearly cancelled, and what it found in the zone, in one of the less celebrated applications of its extraordinary capability, was evidence that the assumption of emptiness was wrong. The galaxy we live in is larger in its complexity than the incomplete view allowed us to see. The neighborhood we inhabit in the cosmic web has structures we did not know about. The satellite system surrounding our galaxy contains members we did not know existed. The streams of past mergers thread through places we could not examine. None of this is cause for alarm. It is cause for the opposite. It means there is more to discover, more hidden in places we have not yet learned to look. The zone is one example. There will be others, and the tools being developed to look into those others are already being designed and debated and proposed, drawing on exactly the lessons that Webb's zone observations are teaching. The zone is not done giving up its secrets. Webb opened a window. Future instruments will widen it. The observations Webb has made of the zone of avoidance, the new star clusters, the hidden galaxies, the anomalous glow, the stellar streams, the dark matter traces, are the beginning of a program, not its conclusion. Each discovery raises specific new questions that require specific new capabilities to answer. The most immediate next step is spectroscopy. Webb's zone discoveries are primarily photometric, based on measuring the brightness and color of objects in infrared images. Photometry tells you a great deal. It reveals distances, temperatures, compositions in broad strokes, and clustering properties. But it does not give you precise velocities. It does not give you detailed chemical abundances. It does not confirm a galaxy identification with the certainty that spectroscopy provides. Follow-up spectroscopic observations of zone objects are already being planned. Some will use Webb's own spectroscopic instruments, its near-infrared spectrograph, capable of measuring hundreds of objects simultaneously, is suited for exactly this kind of follow-up work. Others will use large ground-based telescopes, equipped with infrared spectrographs, targeting specific objects that Webb's imaging has flagged as high priority. The stellar stream candidates in the zone require velocity measurements to confirm their nature. The supercluster candidate behind the plane requires spectroscopic redshifts of member galaxies to verify its distance and mass. The dwarf galaxy candidates require stellar velocity dispersions to confirm gravitational binding. These are tractable programs, requiring dedicated observing time but not new technology. Beyond spectroscopy, new survey instruments planned for the coming years will contribute to zone science in complementary ways. The Nancy Grace Roman Space Telescope, currently scheduled for launch in the late 2020s, will conduct wide-field infrared surveys of the entire sky, including the zone, providing a statistical census of zone objects across areas far larger than Webb's targeted observations can cover. Where Webb goes deep in small fields, Roman will go wide across large ones. The Square Kilometre Array, a next-generation radio telescope being constructed in South Africa and Australia, will conduct radio surveys of the zone at resolutions and sensitivities far beyond anything currently available. The unidentified radio sources in the zone, the objects with no infrared counterpart, are exactly the kind of target that a more sensitive radio telescope can characterize. Better radio data means better cross-matching with Webb's infrared catalogue, and better cross-matching means fewer objects of unknown nature. In the longer term, space-based X-ray observatories and gravitational wave detectors will contribute their own perspectives on the zone's compact objects, the neutron stars, magnetars, and black holes hiding in the galactic plane. Each wavelength adds a layer to the picture. The cumulative effect of all these future observations will be a zone of avoidance that is no longer avoided. A region that was once marked as a gap, a blind spot, an area to skip over when building catalogues and maps, will become one of the most comprehensively studied regions of the sky, precisely because it held so much that was hidden, and because uncovering hidden things is the core impulse of science. We looked into the place we could not see. We found it was full, and what we found there is changing the way we understand the galaxy we call home, the neighborhood we inhabit in the cosmic web, and the long, violent, complex history that brought all of it, including us, into where we are now. The blind spot was never empty. We just needed the right eyes to see inside it.